G'day guys, this video is going to look at the 2-star questions of chapter 22 for Walding. Note that some of the later questions are still 1-star questions and you'll want the 1-star video for that. So our first 2-star question for this chapter is question 25, and we have a circuit diagram below. And we're asked to find a few things about it first. Now, it asks us to find the battery voltage. It wants us to find a circuit current at 3 different points, labelled X, Y, and Z, and wants us to find the reading on the voltmeter that's in the middle of our circuit. So I'm going to redraw that out first. We've got our battery. I'm just going to draw one section. I've got a resistor, another resistor, and then another resistor there, and that's a 2 and 8 and a 4. That also gives us 2 of our points X and Y there and there. Now heading up here, we've got another resistor, and this has a voltmeter here in parallel, 16. There's our 3rd point Z, and we have an ammeter with a reading of 4 amps, round to another resistor at 16 ohms, and finishing off. Now the first thing the question asks us to find is the battery voltage. So what does V down here equal to? And we could theoretically work this out with a very long set of simultaneous equations in order to set up all the relationships between these resistors and the currents, etc., and the stuff that we know, but I think that's too hard. I think that's really annoying, a crap way to do it. Instead, what we're going to do is just work out step-by-step little bits that we can figure out, and once we know every voltage and current used on every single one of these resistors, so these 5 resistors here, then we'll go back and figure out these other things. And one other thing I'm going to do to help visualize this is to draw this picture again, but without this very neat squareness to it that I think makes it harder to see. So I'm going to draw it side on, and I have a couple of resistors in series with this battery, and that comes around to another resistor before coming back, and that's my 2, my 8, and my 4. If we look at our other 2 resistors, they are in parallel with this 8, so let's draw those in. 16 and 16, and I know that there is 4 amps of current leading into this first 16. 4 amps into here. Now I like this diagram a bit better, because now I can see, I was thinking about resistance equivalences, that I could see, oh, well, I've got these 3 things are in parallel with each other, and once I work out that big chunk, I've got these 2 bits in series with it. And we also want that voltmeter, and the voltmeter is going between the 8 and the 16 on the picture, and what it's really doing is it's just working out the voltage before and after this huge section of parallel circuitry that's going on here. So I'll still stick it here in the middle, but all it's asking for is what is the voltage from here to here. And our 3 points on here, well, X is going to be down here, it's easy to put on there. Y is after the 8 ohms, but before the other bits join back up. So it has to go there, not here, but here. And Z is right here. Okay, let's give them names. We'll call this one R1, R2, R3, R4, R5. So that way we can use current 1, 2, 3, 4, 5, etc. and voltage 1, 2, 3, 4, 5. Let's start off with current with resistance 1 here, because this is the only one we have any information. We have our 16 ohm resistor, okay, our R1, and we have our 4 amp current running into it. So have our current equals 4 amps, and our resistance equals 16 ohms. And from that we could work out a voltage going across it. Remember, V equals IR is going to equal 4 times 16, so it's going to equal 64 volts. Right. So I know now that from this point to this point, 16 volts has to be used up. And the good thing is now we can see really clearly that this, and this are all parallel, which means all of these have the same voltage. So remember, I've said this before, but parallel equals same voltage. So therefore, R2 equals 64 volts. Sorry, not R2, V2. V2 equals 64 volts. We call that R3, so V3 will equal 64 volts. And the voltmeter equals 64 volts. And that was one of the things we actually wanted to work out. That was actually question C of this, part C of this question. So we've done C before we've got anywhere near A, let alone B yet. We could work out B next, but we're still going to need A eventually anyway, so we'll do A next in this case. Alright, so remember parallel circuits, sorry, it was very late here. Parallel circuit elements always have the same voltage being used. Okay, let's keep going through this for the moment. Let's look at some current stuff now. And now that we know the voltage going across R2, we can work the current going across R2. We can then work out the current going across R3 as well. Because if we see here, we've got this circuit junction where it goes in this way, and it goes up there, to there, and all the way up to the top. So once we know all those currents, we'll be able to know the current coming through this part and this part, which will give us some answers here. So we're actually going to work out a section B well before section A. So there was part C. So the current on 2 is going to equal voltage of 2 divided by resistance of 2, which we know is 64 because we worked it out over here, and we know the resistance is 16, so it comes out as 4 amps. When 2 resistors are in parallel and they have the same resistance, they're going to end up having the same current as well. I3 though is going to equal 64 divided by 8 because it's a different ohmage, which will then give us an 8 amp current going into it. Now, remember our junction law. We know that all the current that flows out of a point must equal the same that flows into a point. And so we've just established here that from this point that leads to R1, R2, R3, we've got a 4, we've got a 4, we've got an 8. Well, 4 plus 4 is 8, 8 plus 8 is 16. So that means the current over here, if I was to put an ammeter here, it would equal 4 plus 4 plus 8, which is 16 amps. We don't have an actual marking on it, but we can talk about R4, which therefore tells us current coming out of resistor 4 equals 4 plus 4 plus 8 equals 16 amps. And that means the voltage in 4 must equal 16 times 2, which equals 32 volts. The good news is the current going the other way around will also be the same. So therefore I5, oops, that should be a 5. I5 equals I4 equals 16 amps. Voltage 4 is going to equal, pardon me, 16 times 4 ohms. So remember V equals IR. Let's see, equals 64 volts. Sorry, that should be volt 5. So now we know every bit of voltage being used up around every element and every bit of current on every bit of element. So now we can actually work out B as well, because if we go back through all of that, we see that for point X, X is right after that 4 ohm resistor, which we called resistor 5. We just worked out the current for resistance 5 was 16. So X must equal 16 amps. For Y, we saw that it was right after the 8 ohm resistor. So if there was for current 3, 8 amps going through it, then there must be 8 amps coming right out underneath it. So that tells us that Y must equal 8 amps. If we go back up to Z, the Z one, we see that Z was just right after R2. We worked out the current of 2, which was there, so that's 4 amps. So therefore, Z equals 4 amps. And there are 3 correct answers. Now let's go to A. So remember that whatever voltage is given here in our battery must be used up as it goes around a loop. Now that loop could go R4, R1, R5, could go R4, R2, R5, could go R4, R3, R5. But we already know each of these things are 16 volts, so it doesn't matter which one it goes through. So let's just, all we need to do is add the voltage for one of the paths. So if we go back to here, our battery voltage is going to equal voltage across 4 plus the voltage across 5 plus, let's say, the voltage across 1. Doesn't matter which. 5 was 64, 4 was 32, and 1, we scroll back up to it, is going to equal 64 as well. And there we have our battery voltage. 64 plus 64 is 128, plus 2, 130, so 160 volts. And we're done. That's it. Alright. An automatic washing machine is labelled 240 volts, 960 watts. Let's write those down. So we have 240 volts, 960 watts. Remember, watt is the unit of power. Exactly, watt is the unit of power. Sorry, stupid joke. Let's label these. So we've got a voltage, so we're going to give that the symbol V. We've got a power, that's going to be the symbol P. Part A, what's the current? Well, we have a relationship between voltage, current, and power, and that is P equals IV. So if we substitute that in, we get 960 equals I times 240, or that I equals 960 over 240. 960 over 240 equals 4 amps of current. If we go to B, what's the resistance? Again, we have a relationship between V, P, and R. Oh, we could use Ohm's law. We could use V, I, and R, since I is a nice integer number. Anyway, let's use that. V equals IR. 240 equals 4R. Redo that I, because it looks like a plus minus sign. So 240 divided by 4 equals R. 240 divided by 4, let's see, that's going to be 60. 60 ohms. And we've got our answers. Let's head on to 27. A set of decorative Christmas lights consists of bulbs labelled 12 volts, 1 watt. Okay, so we've got a 12 volt, 1 watt, that's for the bulb. If this set is designed to operate from the AC mains, determine the following things. Let's give these some symbols. V equals this, P equals this. We also have the mains involved, and the mains always have voltage 240 volts in Australia. Okay, so let's look at question 1. How many bulbs are there in the set? Well, we're giving it 240 volts. If we were to set this up in parallel, so each of these bulbs were like this, and it was coming from 240 volts, all of them are going to receive 240 volts. question is though, well, what is this thing rated at? This thing is rated at 12 volts. If you pump 240 volts into a 12 volt, you're not going to have a good time. So it can't be parallel. So it must be series. So it must look something like this. 12 volts, 12 volts, 12 volts. Now in series all we do is we add the voltage together. So what I'm trying to find is, well, really, how many groups of 12 will go into 240? Because that's going to give me 20, which is the number of bulbs on our light stream. Okay. So let's go to B. Where am I? What is the total power consumed by the set of lights? Well, each light uses 1 watt, and there are 20 light bulbs. Therefore, 20 watts, because it's 20 bulbs times 1 watt per bulb. What is the average voltage drop across each bulb? Well, we've been told what the voltage drop across each bulb is 12 volts, because that's how much a bulb uses, or that's how much this bulb uses. Sometimes some of these questions are right there in front of you, and you just need to give yourself a bit of trust, or double check the answer at the back before you go and do it. What is the current, and what is the resistance of each bulb? Okay, well we know that P and we've got these two values up here, V and P. We can work those out from that. So I, we just said, was V divided by P. Sorry, and P divided by V. That's what we had up here, wasn't it? Yeah, P over V. It's going to equal 1 over 12 equals around 0.083, I think. Yeah, because the answer is 83 milliamps, which would be 1, 2, 3. Yep, good. Resistance, so P equals V squared over R equals V squared over P, equals 12 squared over 1 equals 144 ohms. Done. Yeah. Nice and straightforward for that one, I believe. Okay, let's keep going. The question has 145. That must be a typo. 28 and 29, they're both one-star questions that have been answered in the previous video. Let's go to question 30. Interesting question, this one. Now we've got a graph below there, and it's got two lines on it, A and B. We see that A is a straight line and B is a curved line. And looking at the X and Y axis, we see that there is a potential difference V and a current in milliamps. So voltage and current there. So the first question is asking us, what is the ohmic resistor? Now, in a case like this where you're not sure of what a word should mean, you should go back and have a look. And if you look back in the previous part of the text, or if you do a search for ohmic resistor on Google, you'll find, or maybe ohmic resistor graph, because you know this question is involving a graph, you would find out that ohmic resistors always appear as straight lines when plotted for voltage against current, until they hit their limit and then they blow up. Non-ohmic resistors are curved because their resistance will change depending on what voltage and current is being given to them. So, therefore, looking at that, we see that A is straight. A is straight on VI graph. Therefore, ohmic. Nice and straightforward. No, nothing more than that needed to be, because this sort of question would be the cognitive verb determine, because you just need to look at the graph and tell me which is which. It's like a application of knowledge type question. If A and B connected in series and a current of 200 milliamps passes through them, what will be the total potential difference across A and B? So this time, what we're going to do is use this current I equals 0.2 amps or 200 milliamps, find the resistances and treat them with how we would in series to then work out the voltage across them. So let's work them out. So resistance of A if you go to the graph and you just find 200 milliamps on the bottom axis, the x-axis, and scroll up until you hit the line A, we see that it's about 12.5 volts at this point. Okay, and if we go to our B line, sorry, I don't know why I typed resistance of A, should be typing voltage of A, voltage of B. We want to look at our current of 200. We see that's about 2.5 volts. So therefore, total voltage is going to be 12.5 plus 2.5 equals 15 volts. Okay, so because we're asking for what is the potential difference across both of them, that's the important bit, and we are trying to, when we have things like this, we begin to add them together in series, because each one they're going to be using voltage up, like we practiced that, like we did in that first question, question 25. All we do is add them up. Now the text at the end gives us 12.5. I guess maybe for B it might be 2 volts instead of 2.5. Sorry about that, guys. So yeah, I wouldn't, if you gave me 15 volts on a question like that, I would not mark that down, because to me that graph, you know, it's not really marked out to show, oh, this is 1, 2, 3, 4, 5 up through there. So the difference between 2 and 2.5 on such a small graph, really too fine a detail for me to worry about. Question C, if A and B are joined in parallel, so this means they need to have the same voltage. Remember, parallel things have the same voltage. What potential difference across them, so what voltage across them, would produce a current in A equal to half the current in B? Okay, so we want to find a voltage line and look where A and B are, lines A and B, and draw them down to the current section to find a current where they are half and half. So I'll actually draw this out for this because it will help us to see it visually. So something like that, and then like that. And we've got 100, 200, 300, 400, 500, 400, 500. We had 5, 10, 15, 20. So what we're asking here is, like, let's choose a voltage, let's say 10, and go across until we get to here. That's around 200 milliamps. And then keep going across to here. What we see, that's about 450 milliamps. It's okay, but not perfect. Okay, so we're looking for a place where A is half of B, where the current on A is half the current on B. So if we look along that, and eventually you'll find the point of 15 volts. And if we scroll across 15 volts, we get to around here in the middle, which is pretty close to 250. We keep going across to here, get that it comes up at 500 milliamps. And that would make the two currents equal to half, or sorry, A equal to half of B. So 15 volts is going to be our answer for C. Yeah, good question, but really just involving you to interpret and use a bit of logical reasoning and application of stuff to it. What is the resistance of device A, and how does this compare with the resistance of B with a voltage of 15 volts applied? So let's go to Ohm's law. V equals IR. So what we have here is we have Y equals mx plus c. C is 0 in this case. Okay, there's no c. But we know that voltage equals y because that's on the y-axis, and current equals x because that's on the x-axis. So that means that resistance must equal the gradient. And this is a fairly common data interpretation type skill. For year 11s, this is something you probably haven't seen yet. Year 12s, it should be reasonably familiar. In fact, I think we did an experiment on this. So all we need is the gradient of our line here. And the rise over run, well, the rise was equal to 25 volts with a run of 0.4 amps. And 25 divided by 0.4 is going to give us, where's my calculator? There it is. 25 divided by 0.4, around 62.5 ohms. Okay, and that's for resistor A. Let's do resistor B. Now for resistor B, that told us that voltage equals 15 volts. And we're going to need to work out the current. We can see that that's going to equal 0.5 amps. Let's do the same thing. Voltage over current equals resistance. So 15 over 0.5 gives us 30. No, sorry, we won't want that. We want the tangent at that point. Sorry. I hate doing tangents on these things. If I look at this, it looks to be, say, reasonably straight up towards B. So let's do it from that point up to B. So we have 15 voltage 1 is like that. Current 1 equals 500. Voltage 2 equals 25. Current 2 equals 600. 0.6. Let's change that. Sorry, 0.5. Run it in SI units. So rise over run. So for a rise of 10, we're going to divide it by 0.1. Look, that's going to give us 100. Resistance B equals 100. The first resistance B we had was equal to 30. If I just took the point, let's take the average of those, 100 minus, plus 30 divided by 2. Great, so the average there, if I take the average of those, 65. And the textbook is actually saying at the end that they should be roughly the same. If you were to do a much better gradient at that point, or even use an equation to then work out the actual, or use the numbers there to work out the formula of the line, for example, it's asymptoting 0. Looks like it could be a power curve, perhaps. Could be a quadratic equation. It could be like that. But there's no reason you couldn't use the points to work it out. I don't like doing those things. It's really sucky, but it is what it is. But the emphasis I really want you to take is that it's the gradient you want on a voltage current graph to work out the resistance. Question 31. Resistance of 1.5 meter length conductor was measured as a function of temperature. The following data obtained. Blah blah blah. Now I've already graphed this out before. So I'm looking at my graph here, and we see that it sort of looks like this, where we've got temperature on the y-axis, because resistance on the y-axis, because resistance is the thing we are measuring in response to temperature, and we see that it crosses and has a line like that. Okay. Now the important bit is though that y equals 0.000133x plus 0.0329. And the good thing is we can kind of see that 329 there because it is very close to that intercept point at 0 degrees. Note I've converted it to just numbers instead of scientific notation. Alright, so we've got our graph. We've got our line of best fit. And the second step of it is that we want to find the value of alpha. And the clue for this is that there is a relationship between resistance and temperature, and that the resistance at a temperature equals the resistance at 0 outside of 1 plus alpha change in temperature. And what we want to do is somehow match up this equation to this equation. The first thing we do is I'm going to expand that bracket. So RT equals R naught, because R naught times 1 is just going to be R naught, plus R naught alpha delta T. And now we're starting to get a little bit y equals mx plus c. Here's our y. Resistance is a function of temperature. Here's our x. It's the temperature. Here's our c. It's just the plus CL at the end, which means that this bit here has to be equal to our gradient, our slope. So that means that M equals resistance naught alpha, but it also equals this number we got from before, 0.000133. Now, I did all this in Excel. You can get the slope. There's actually a slope function that will give you a slightly more precise slope than using the gradient function on Excel, on a graph, on a trend line. I did that. I got 0.001. Sorry, 0.0001. I wasn't quite happy with that, so I went and used equal slope, and then follow the prompts to work out the slope or something. That gave me a bigger number, or a more precise number. So I was happy with that. So here's the interesting bit. We have that resistance naught times alpha equals this number. But what's resistance naught? Well, good news is resistance naught comes from the data table up there. Resistance naught equals 0.335. So if we were to rearrange that, then we get that alpha equals 0.000133 divided by 0.0335, which equals 0.0039. Let's do that a little bit. 63, and the unit for that would be ohms per degree Celsius. Let's go degrees Celsius. Okay, and finally on to part C of this question. We want a conversion formula from resistance to temperature. Well, the good news is I can't already have one. It's the trend line. So it's just going to be that. From resistance to temperature. Sorry, we're going to need to rearrange it. Okay, this is what I want to do. I want me to take this formula and rearrange it. So let's write that out again. RT equals R naught outside of 1 plus alpha delta T. Okay, let's do our rearranging. So we want to try to get delta T on that side. First thing first, let's divide by R naught. RT divided by R naught equals 1 plus alpha delta T. We've got this plus 1 sitting off to the side here. Let's subtract that. RT over R naught minus 1 equals alpha delta T. And finally, the last thing is get rid of that alpha. So let's divide that over by alpha. So RT over R naught alpha minus 1 over alpha equals change in temperature. We could redefine change in temperature, for example, and work out, write it as temperature final minus temperature initial, and then move the temperature initial to the other side. However, if we let the change in temperature just be from 0, then we don't need that anymore. So I'll rewrite that equals TF minus TI. Let TI equal 0. Therefore, RT over R naught alpha minus 1 over alpha equals the current temperature. So with this, actually, we could design a clock if we knew the resistance of at a certain temperature, and we could use that, figure that out using Ohm's law, run some current through it, work out, or offer voltage, work out the current that goes through it. We could then divide it by the conductivity or the resistivity of the metal, subtract the reciprocal of that, bang, you've got a clock, or you've got some sort of temperature device that is based off resistance. Okay, how's our time going? Not too bad. We've got 2 more questions here, 33 and 34. Note that 32 is a 1 star. It's in the previous notes, previous video. Question 33. Design and draw the diagram for a 2-way model circuit that will operate a lamp from 2 different locations in a house, from upstairs or downstairs. So if you've ever had a long hallway, you might have a switch at either end so that you can turn on and off the light from either end, or maybe a stairwell, and that way you can turn the light on at the bottom of the stairs and then turn it off at the top of the stairs when you get up. Let's draw our light bulb first. is our light bulb, and it does need to connect to some sort of power source. Now the switching system for this is what we call a three. We need two three-way switches. It looks something like this. Now this one connects to here. I'm just going to do dashes for this so that we can see it. So right now this would be on. You can see you get to one end of the house and you switch it to off so that this line here goes down to here, and we can see now the electricity doesn't flow, so it would turn off. You turn it back on, because you're walking back down the hall, bang, your switch turns on, you get to the other end of the room, and bang, you turn it off, switch it to the other side. Now you no longer have a circuit going on. So this is what we call, these are what we call three-way switches. And while I know the circuit diagram for this doesn't exist in your textbook anywhere, these sort of things are worthwhile looking up because you can find a whole bunch of examples on this. But that's how we do a two point switch, where they're both in one position. We've got current, you switch one to the off, they both break, it stops because the current can't flow through. Both of them need to be in the on position. And the good news is that if I do, maybe I go, it's bright and I don't need to turn it on, and I go up the other end, and then later in the afternoon coming back and it's dark, I can just switch this to the other side, and even though it was in the off position, now it's been put into the on position. 34. This question was annoying to me. Electric kettles range in power from blah to blah. The rating is usually stamped underneath. Table has been taken from a magazine and compares the performance of 10 different cordless kettles. Plot a graph is the first bit between power consumption and boiling time for 1 litre of water. Note we have boiling time for 1 litre of water, and we have power consumption there. Now they've said that power consumption is going to be the x-axis in this case because that's the thing that it does. It draws that much power, and we're interested in seeing what does that do to the boiling time. And if you go and plot all those, you see roughly a graph that kind of looks like this, so something like that, if you put a trend line through it. So it could be, if you wanted to, you could roughly say it's linear or inverse linear. There is some thoughts that maybe it could be a power curve. I wouldn't say it's a power curve to me because, I wouldn't say it's a linear line, because if I keep tracing this all the way back to, a very low power consumption, like a zero power consumption, it'll actually cross the x-axis. If it crosses the x-axis, that's saying if I add zero energy to something, it will boil. We know that can't be true. So we should expect, realistically, something like this, okay, because that should never hit zero. Or at least it should never cross the y-axis, because if it crosses the y-axis, it's telling us that when x equals 0, when power equals 0, that there must be a, this is going to be time, there must be some, time it takes for it to boil, even though we know it doesn't do that. Okay, so inverse linear from the data, but inverse power in real life. Okay, question B there. Estimate the boiling time of a 1600 watt kettle and a 2400 watt kettle. Now I chuck this into thing now because those two numbers are just outside of the scale of the graph. I'd just use a what's what I'm looking for? The trend line to work that out. And what I'm going to use is my trend line. Y equals negative 0.0859 times P, because I have power on the x-axis, plus 361.52. So that means whatever power I put in is going to be some negative number. I add this number, I'm going to get myself a time in positive seconds, probably. However, if the power is too big, then we would end up with this going below there, and it would be negative time to heat up, so obviously it can't be right either. Hence the probable exponential curve. So I'm going to let P equal 1600 and P equal 2400. Now, being as I've got the formula there for you, you could work out, instead of Y, let's use T for time, because that's what it's finding for us. That equation I got from making a trend line in Excel. Trend line Excel. It's not some fancy formula you need to remember. It's just for that data set, just from Excel. Okay, the last bit, once you work out the efficiency. Now, realistically, to do this, if you haven't done thermodynamics with knowing the heat capacity of water and stuff, you can't do this question. So this is not a question I'd give a Year 11 student who's not done thermodynamics, because that's your Year 12 subject. The current Year 12s, you most certainly could do this question, but take from that what you will. The thing we want to work out is the power that is coming out. We have the power going in, it's in that power consumption column, but we want the power out. And the power out, remember, equals energy over time. We've got the time, it's from that boiling time of 1 litre of water. The question is now what is the energy? And the energy for heat capacity is equal to mass times specific heat times the change in temperature. The mass in this case is going to equal 1,000 grams, because that's 1,000 millilitres, it's 1 litre of water. And the specific heat capacity of water is 4.2 joules per gram per Kelvin. The delta T, well, they tell us that it starts at 25 degrees. Boiling water goes to 100, so let's say that that's 75, and we would divide that by the time. Now, if you do that for every single one of those examples there, so you've only got different time, you're going to have the same energy on top, but you have different time, you would then be able to work out the efficiency for each. And by comparing the efficiencies, note that it says a hint, the efficiency for the Lindner Superboiler is 84%, it's not at 79%, I don't know where that's coming from. However, if you look at all the efficiencies compared to the compared to power, so the highest power one is 2290, and that has an efficiency of 86% on my table. The next one is 2240, but that has 83%. And there are some 85s and 89s, which are all, 85s and 84s, which are all the way down the other end of the graph, near the 1.89 kilowatts and then 1.91 kilowatt power consumption. So there does not seem to be a trend between how much power it uses and how efficient the actual jug is. Alright, those are all your 2-star questions. Remember, 3-star questions can be found on the seniorphysics.com website, and you can always email me and I can give you hints about them, but I'm not going to explain how to do those completely. Okay, have a good night, and I will see you next time.